welcome back to this session, and what we're going to talk about today is going to be the Earth as a planet. So I want to kind of go over the characteristics and properties of the Earth, and then we're going to use that to kind of compare all the other planets too. So Earth is our standard. So let's talk about the Earth as a planet. So keep in mind, guys, I want you to think about this as we compare all the other planets that we're going to talk about back to the Earth. So let's first talk about the uniqueness of the Earth. Certainly right now, and I do stress as of right now, the only planet that we know of that has life on it is the Earth. Now, there are some other possibilities in the solar system, and as we get to those areas, then we'll go ahead and talk about those possibilities. But the one that we know for sure is Earth is the only planet that has, and hopefully it's intelligent life that we have on it. Then we have four big spheres, which is the hydrosphere, the atmosphere, the geosphere, and the biosphere that all are going to interact and combine to give us the kind of thing that we see here on the Earth today. We know that water coexists in all three states under the same atmospheric conditions, and that's very unique in terms of looking at all the other planets. And that's due to where we are as well as a combination of other conditions. And then we know the Earth has vast amounts of liquid water. We think that liquid water in vast amounts is required if we're going to have life. So we're going to look at every other planet and see what their conditions are relative to water. Now, if we think about the energy that powers the Earth, it comes from three sources: the sun, tidal effects from the moon and the sun, and then the internal energy of the Earth. Now, we talked about, when I did the intro last time, that the Earth itself is about 4.5 billion years old. But if we actually talk about the age of the surface, then that's less than about 100 million years old. And it's because that surface is continually undergoing all kinds of geological activity. Now, we know that the only other planetary body in the solar system that is actually changing a whole lot more than what the Earth is Io, and that's one of the moons of Jupiter. And we're going to find out that it's basically giving off volcanoes every time you turn around. It's extremely active. If I think about the surface temperature range on the Earth, we go from about 136 degrees Fahrenheit down to a low of about 129 degrees Fahrenheit. That gives us an average temperature of about 48 degrees Fahrenheit. And we think that temperature has changed a little bit in the past in terms of the average, and is probably changing in the future. Exactly how, we're not sure. There's still all kinds of hypotheses that are going on as to whether we really are undergoing global warming or not. And certainly whether that global warming is made from man-made sources, natural sources, or a combination of both. Now, remember I said that we have a maximum temperature of 136 degrees Fahrenheit? This is taken where that maximum temperature was reached. Just to give you a couple of shots here of that. It's over in Iran. And you'll notice the incredibly different designs that you have of the rocks and the colors of the rocks. And that's because of the evaporation of the water. And what you have after that evaporation occurs is then the salts that are left behind. And then now we're going to go to the other extremes, where we're getting our really low negative temperatures, and this is down in the Antarctic. And this is occupied about 365 days a year, so you can imagine what this would be like trying to get outside when you've got temperatures of about minus 130 degrees. So now let's look at the Earth from space. And as we talked earlier, you know that you're going to see a variety of blues, which is from the water, whites, which is from the clouds, and then the browns, which are from the oceans. And so this is our blue marble, as it's sometimes called. And you can see the oceans there. You can see some of the land masses up toward the top and some of the cloud structures then that cover the Earth. Now we know that forces are continually reshaping the Earth. We know that the surface has been twisted and deformed and folded. Also has been faulted there. Water and wind then are causing erosion and weathering. And we know that the Earth's interior is under tremendous heat and pressure, and that causes continual upheavals of the surface. If you've ever experienced an earthquake, well, you've then experienced some of those tremendous heats and pressures that are underneath the surface. If you have never downloaded Google Earth, let me suggest that you do so now. Google Earth then allows you to basically go any place on the Earth that you want, as well as it gives you a sky view and some other things. But Google Earth really gives us a feel for what the Earth looks like from space, and then you can drill all the way down to what the surface looks like. And if you get in some of the larger cities, then you can also go ahead and get a 3D view of it and basically walk through the cities there. So like I said, guys, if you've never downloaded or had a chance to look at Google Earth, definitely go ahead and do so in the near future. So let's look at the Earth from space. And so this is probably one of my favorite pictures of the Earth from space. It's obviously taken from the moon. Now, as you look at these pictures, I want you to see if you can see evidence of life on that surface. I certainly don't at the distance that I'm looking at it right now. All I see are the blues and the whites with maybe a little bit of the brown surface there to give you a feel for the fact that there are different textures on there. If I looked at this over a period of time, I would notice that the features do change. But I really can't see any activity of life at this scale. Now I'm in the Skylab, I'm at the International Space Station, looking out at the sun coming up from the level of where the International Space Station is. So you can kind of see the layers there. Now here, if I look at this picture, we definitely do see evidence of life. And so these are taken from the Landsat satellites. And you're actually looking at Los Angeles and the area around Los Angeles. And then if I look back within that very flat area that you could see, then I've got some hills, some valleys back there, and we actually went back there, you'd see where you have some of the fault lines. Now, what do you think this might be? Well, I've had people guess, and they tell me it might be a star cluster out in space or something like that. But in reality, guys, we're looking at the city of London at night. You can see the very center of London where you've got this incredibly concentration of white lights. And then on either side, then you're getting areas that are very, very black. And those are some of the parks that you see in downtown London. And then it's pretty obvious one of the main highways or thoroughfares around London is in what you see toward the bottom that looks like that nice white line that's going around it. But that's what London looks like at night. And that would be the same kind of picture that you would see of any large city at night. Now, we know that we have evidence of impact craters on the Earth, and this is a very old impact crater that has been filled in with a ring of water. Still have the land in the middle. And so a lot of these impact craters we actually didn't discover until we were able to look at it from the Skylab satellites or from the level of the space station or the Apollos or whatever happened to be up there at the time. Anybody recognize this city? Well, if you're from Missouri, you should. And let's say you're from the eastern side of the state, and what you're looking at is St. Louis. You can see the rivers coming in from the top, and they're going to collect together on that upper right side to go ahead and form the Mississippi. And then you see then the Mississippi coming down. And you can see the waterfront there. Now, it's kind of hard to tell that you're really looking at individual buildings or things like that. I mean, you obviously can't see those from this level, but you can at least go ahead and see that it looks like it's some kind of industrialized or man-made situation. Now, the three pictures I have here are looking at the Great Flood of 1993 in St. Louis. So you have on the top one to the left, you have before. To the right, the top right one you have is after the flood. And then the one at the bottom is during the flood itself. And notice how big that river has gotten. You can see where the Mississippi and the Missouri and all the rivers come together and then flow down through St. Louis. And if those of you that remember the flood of 1993, you know that it got all the way up to the bottom of the arch during that time. So you had completely flooded then the landing down in that area all the way up to the level of the bottom of the arch. So there was some concern that the arch itself would be flooded. Here you're looking at a volcano that is active. And then the next several shots are just different pictures of the Earth from space. Now, I want you to try and see if you can guess where they are or what they are. And then if you go on Blackboard, I will have a list of what those were. But right now, I just want to see if you can kind of guess where they are and what you're looking at. And it gives you a whole different feeling when you're looking down from space. Okay, so now let's talk about the structure of the Earth. I just had you look at several examples of the Earth from space. So what is that structure in terms of looking at the Earth? How is the Earth formed and how is it put together? Well, we know there are basically three different parts of the Earth. I mean, think back to your probably 6th and 7th grade classes, guys, in science. You talked about the crust, the mantle, and the core. Well, that crust is that really thin top layer that happens to be real important to us because that's where we live. And the mantle is that middle layer. And then we have the core, which is all the way at the core of the Earth. And we have two cores. We have an inner core and an outer core. And that outer core becomes extremely important to what's going on within our magnetic field. So this gives you kind of a schematic of what the Earth's construction looks like. So you've got the crust there. And notice that it is a really thin layer. Then you've got the upper mantle and the kind of mantle itself. And the reason they divide those two is because you've got big convection currents that are forming in that mantle layer. And those convection currents help to go ahead and move the crustal plates that we have on the surface of the Earth. It's because that heat gets carried up to the top. It's able to then go ahead and move that mantle, which in turn goes ahead and moves the continents and the crustal plates that are on that surface. And then we have both the inner core and the outer core, and the outer core is going to be liquid. It happens to be liquid metals. Remember that chemical differentiation due to being heated? Well, you have those really heavier elements that have fallen toward the center because they're heavier. And so that's where we have that nickel and iron core. Now, how do we study the interior of the Earth? Because we certainly can't go ahead and drill all the way down to the core. Well, we can certainly sample the crust, and that gives us a feel for what the crust itself is like. We have earthquake waves, and as these earthquake waves go off, then they will travel through both solid, but when they get to a liquid part, then they go ahead and are stopped by the liquid. So by looking at where we are reading those earthquake waves, gives us a feel for when it went through relative to solid material or whether it was absorbed within that liquid material and it wouldn't go any further. We try and understand what's going on with the interior by looking at the geological activity that we observe on the surface. We also have a rock cycle, which we'll talk about in just a minute, and look at how those rocks are changed, which helps us see what's going on inside. And then we have the magnetic field. Now, as we look at the magnetic field of the Earth, we find out that it's formed because that outer core is rotating. So if we look at other planets and we find out that they have magnetic fields, then something has to be molten liquid that is then rotating, which is providing that magnetic field. So crust has a density of about 3 grams per centimeter cubed. Water has a density of about 1 gram per centimeter cubed, so our density is a little bit higher on the crust than what water is. It does change its thickness depending on what it's under. We know that it's about 4 miles thick under the ocean. It tends to be composed of basalt rock, which is basically cooling lava. And the crust under the ocean consists of about 55% of the total crust. That's different than what's under the continents. Continents are basically made out of rock. So the crust has to be thicker to go ahead and support the heavier continents. So it's about 13 to 45 miles thick under the continents, composed mostly of granites. And that makes sense because you tend to then go ahead and put that part of the crust, the mantle, under much higher temperatures and pressures. So you would expect those rocks that we observe from the crust under the continents to show as being metamorphic rocks. And that makes up about 45% of the total crust. So we've talked about rocks. You probably talked about rocks when you were in the, 4th, 5th grade, 6th grade, something like that. And I bet if I asked you what they were before putting this slide on, you would have been able to tell me that there were 3 types of rocks: igneous rocks, sedimentary rocks, and metamorphic rocks. And so if you think about igneous rocks, those are rocks that are cooled from molten materials. So basically you have rocks or material that is under high pressures, high temperatures, that gets extruded some way, whether it's through a volcano or other mechanisms, and it will go ahead and cool down. And so those are where you get your igneous rocks. And those rocks have certain characteristic looks and certain characteristic behaviors if they're formed from molten materials. And sedimentary rocks are fragments of rocks that have been cemented together over time. But when we show you this sedimentary rock here in just a minute, you'll notice that it's got big chunks of other rocks in it. Well, sedimentary rocks basically have gotten fused together, but there was no heat, so that the chemical characteristics were still retained of the individual rocks. That's not true of the metamorphic rocks. Take a sedimentary rock, change it chemically because of the pressure and the intense heat that you have on it, and so you will see that it's a very different rock than what it had when it started out as a sedimentary rock. So it's changed both chemically and physically. So guys, these are 3 pictures of rocks. I want you to see if you can tell me which one is the igneous rock, which one is a metamorphic rock, and which one is the sedimentary rock. Now remember that igneous rocks are formed from cooling molten material. Sedimentary rocks are formed from individual rocks or pieces of rocks that have been cemented together, basically crushed together over time, but still retain their individual characteristics. And then metamorphic rocks are rocks that have been chemically and physically changed due to heat and pressure. Okay, my guess, guys, is you had no problem at all figuring out which one was the sedimentary rock. So that's our sedimentary rock, as you can see the individual rocks that are still in it. Okay, so that means I've got an igneous rock and a metamorphic rock. Now, which one looks like it's been cooled out of molten material? Well, that right there is our igneous rock. It almost looks like there are areas that were outgassed as that thing went ahead and cooled, and that's exactly what happened. That was a very hot surface. As it cooled, those gases came out of the rock itself. It left those pop marks, things like that. And so that looks pretty, typical of an igneous rock that has been cooled over time. And now I take those rocks, either igneous or metamorphic, and I stick them under a lot of heat and pressure, and I'm going to physically and chemically change the characteristics, and so I get my metamorphic rock. And so that's a picture of a metamorphic rock. So there are 3 very typical examples of an igneous, sedimentary, and metamorphic. Now, we talked about a rock cycle. Well, that obviously means that... Oh, excuse me. That was kind of a surprise. Okay, so we're looking at a rock cycle. Now, the cycle implies that you've got something that continues all along. And so I want you to see by looking at this rock cycle that we don't necessarily go from an igneous rock to a sedimentary rock or to a metamorphic rock. That actually you can form any of the rocks from anything. You can go from crystallization, and you're going to form then your igneous rock. Then from weathering and erosion, you might get a sedimentary rock. Then you put those sediments together and form the rock itself. You've got then heat and pressure that'll get you a metamorphic, and then you melt that metamorphic and you will go back to the magma and start the cycle all the way again. Well, that works for the outside real well. But now when you get to this inside part, notice that, you can go from a sedimentary rock all the way over to an igneous rock. Then it doesn't matter which way you go. So that's what a cycle means. It just means it's continually occurring over and over and over again. This is another way of looking at the rock cycle where you're really getting into that erosion and transportation, that deformation, all those kinds of properties and characteristics that go into making the various kinds of rocks. So don't assume that once you have an igneous rock, it will always stay as an igneous rock. You can go from an igneous rock to a sedimentary rock to a metamorphic rock, back again, or any of a variety of ways. Now what you're looking at here are some of the oldest rocks in the world. This is taken out in Australia. Kind of looks like some of the rocks that you see around here. But by dating those rocks, and there's a variety of dating techniques, then we know that these are some of the oldest rocks on the Earth itself. Also, looking at those rocks, you get the fact that they've been uplifted, and so you get some of that layering. And so that layer at one time was then level, and through various geological processes, things like that, they have been upended as well as then rotated just a little bit. So now we've got the mantle, which is that area right under the crust, and it's the largest part of the solid Earth. Extends about 1,800 miles down, and it's, like I said, more or less solid under high temperatures and pressures. But because it is under extremely high temperatures and pressures, it can actually go ahead and flow and deform even though it's, quote, solid, okay, in that liquid state. I mean, you can put anything under those high densities in terms of pressure and heat, and that solid is going to go ahead and be able to be formed in a variety of different states by being pushed together, chemically changed, physically changed, all of those kinds of things. And our density, because of that pressure, is going to increase from about 3 to 5 grams per centimeter cubed. Now, the overall density of the Earth, remember, is about 5.5 grams per centimeter cubed. And so that kind of gives you a feel for how much of that then, when we figure that density, is from the core as well as the lower part of the mantle. So now we talk about the core. Diameter is about 4,400 miles. As I said, there's an inner and outer core. The inner core is solid, extremely dense, probably composed of iron, nickel, and sulfur. And we know that it's probably composed of that by looking at the density of the Earth. It tends to be about 1,500 miles thick, so of that 4,400 miles in diameter, inner core is about 1,500 miles thick, which leaves the rest of it to be an outer core. And that outer core is a liquid metal. It's basically iron with some nickel, even though generally people talk about it as nickel and iron. But most of it is iron. And then those materials are basically circulating, and because it is metallic, then we are setting up very big, gigantic electrical currents. And those electrical currents then can create magnetic fields, and those then magnetic fields are what we see as magnetic north and magnetic south. Like I said, the outer core is kept in motion because of the motion of the Earth. And that makes sense. You've got the Earth rotating on its axis, so that causes anything that is liquid to rotate as well. Now, what is the difference between magnetic north and true north? Okay, true north is north as measured where all the lines of longitude and latitude then meet. Okay, magnetic north, on the other hand, is where the magnetic north of the compass is actually located. And we find that that has slowly changed over the last several years. So right now, the magnetic north is slowly drifting across the Canadian Arctic. And it's moved about 1,100 kilometers, or about 700 miles in the last century. Exactly why it's moving and why right now it is accelerating, not exactly sure. But we do know that it's moving about 25, at a rate of about 25 miles per year. So that means that magnetic north is physically changing every year. It's moving about 25 miles in 1 year. So that means our compass needle is going to be changing relative to where magnetic is, because that's what it reads when you look at it. It's reading magnetic north, not true north. So this is kind of a picture of the United States and then Alaska and Canada, Greenland up there, and kind of showing you where magnetic north is. Now I want you to think about this picture, and I'm going to go ahead and put a little bit bigger detail to that, and look how much magnetic north has moved in the last 100 years or so. Notice it started down, let me put my pen on, started down here in about 1831, and then has moved to right here by the year 2001. And we find that it is accelerating, so it is moving faster now than it was before. Well, the other problem, not only is it moving faster than what it was before, it seems to be decreasing in strength. Now, we do know by looking at the rock structure within the Earth itself and the various rocks that have been formed that the magnetic field has actually switched polarity. So is it getting ready to switch? Because it is decreasing. So is it going to somehow flip from north to south? We're not exactly sure what's going on at this time. But we do know it is changing. And so they are continually taking a look at it and tracking it so they can find out exactly what is going on and attempt to really understand why and how that magnetic field is changing. Now, it is important that we have a magnetic field. Now, what I've got right here is there's the Earth in the center, and we have things that are called the Van Allen belts. And we find that those Van Allen belts basically help protect us from the solar winds that are coming out from the sun. Those solar winds then get trapped and interact within the Van Allen belts, and you have all kinds of beautiful activity in the sky called the northern and southern lights. Now you can see that the Van Allen belts tend to be squashed in the direction of the sun by the solar winds and then elongated then behind the Earth. I tend to think it kind of looks like a spider there. Okay? It's a good thing because that does protect us then from radiation here on the Earth coming from the sun. Now that also means though that gets directed down toward the two poles, the North Pole and the South Pole, and that's why then when you have the northern and southern lights, that's why they're occurring on the north and southern poles, because that's where then the two parts of the poles come together. Now, these are pictures of the northern and southern lights. Most of these actually are the northern lights, but you'll have the same kinds of things with the auroras down in the southern hemisphere as well. Now, we have found that these are not unique to the Earth. Any planet out there that has a really big magnetic field, and we find these on the gas giants, will show these same kinds of auroras, both northern and southern. So we know that those planets then do have pretty large magnetic fields. The colors that you see of the northern lights represent chemical composition as well as the temperatures. And notice that on this one you can see the stars through those northern lights. Now I would encourage you to check out various videos on the internet of the northern and southern lights, because where I'm showing you a flat still picture, they have these videos of these incredible colors of curtains racing across the sky. Very, very impressive. If you ever have a chance to get far enough up north or down far enough south that you can see them, definitely take advantage of them. We have seen them here in Missouri about 3 or 4 times over the last 30 or 40 years. But that means you've had to have an extremely large flare on the sun to send the solar winds out. And unfortunately, by most of the time that we see them here, we're only seeing a kind of a red sky. We don't usually get to see these incredible colors racing across the sky. Now, true north, like I said, is at the top of the Earth. And it's where all those longitudinal lines converge at the North Pole, or conversely at the South Pole. Most of the time it is covered by ice. However, recently there has been some water that has been sighted there. That gives you a kind of a feel for where the North Pole is. Think about where Greenland is. Okay, from where we were looking at it before. Now, we do know that magnetic north and true north are essentially in the same direction. And man, for what we're talking about here, trying to follow a compass, in the central part of the United States, top part of the United States, it really doesn't matter. The fact that true north and magnetic north are a little bit different. It really only starts worrying about it when you get up extremely far north or extremely south to where you now are looking at magnetic north and magnetic south as opposed to true north and true south. And so magnetic declination is a difference between magnetic north and true north. It generally ranges from about 0 to 25 degrees depending on the location. And right now, we know it's changing. And so all the charts then that have been prepared for several years that give you the distance between true north and magnetic north are having to be rewritten because of the fact that magnetic north has changed. So now let's go ahead and switch to looking at the Earth relative to plate tectonics. Because one of the other unique features about the Earth is the fact that no other planet has plate tectonics. Now on Mars, we are going to see a tectonic crack in the surface, but it's not the same. We don't have plates on that surface that are moving. Okay, we do have plate tectonics here on the Earth. So what is plate tectonics? Well, that explains how the slow motion within the mantle of the Earth, because remember we talked about those convection currents, can move large segments of their crust, and that results in a gradual drifting of both the continents and the formation of the mountains, as well as other large-scale geological formations. Okay, on Blackboard right now, well, not right now, because right now we're talking here, but once you get a chance, go to Blackboard, and one of the things that I have posted on Blackboard is how the continents on the Earth have changed over time. We're going to go all the way back to Pangaea, which is one of the supercontinents, and look at how that has changed over a period of time due to plate tectonics. And it gives you a whole different feel for how long and how much those plates have moved. Now we have about 7 major crustal plates. And so unfortunately, those 7 plates are moving in different directions. And there are 2 important components of those crustal plates I want you to know. One of those is the Pacific Ring of Fire, and the other one is a mid-ocean ridge that runs down the middle of the Atlantic Ocean. Now remember I said we have about 7 major plates? And we have the Pacific Ring of Fire. Well, this is showing active volcanoes, the plate tectonics, and the Ring of Fire. Now, find North America. Okay, we're sitting on a plate. It's called the North America plate. And notice that the edge of the plate runs down the Pacific side of the United States, basically the western side of the United States. Well, it runs then up toward Alaska, over to Japan, down the side of Japan, and all the way then down past Australia, where you can see then that Pacific plate down there at the bottom. And so that entire plate is moving. Well, we find that along the edges of that plate is where you're going to have a lot of active volcanoes and a lot of active earthquakes. Look at that area around Japan. Look at the trenches toward the top part of the Pacific plate. Look at where you see volcanoes and earthquakes along the western edge of the United States. Well, that plate is moving independently of the other plates. So that causes all kinds of problems in grinding and a tremendous amount of heat and pressure, and that heat and pressure then builds up and will snap, and when it does, we have an earthquake. Or if you've got a lot of heat under there, you get a lot of material that is molten and comes up in the form of volcanoes. So we definitely have a lot of motion around that Pacific Ring of Fire. Now, notice that there are other kinds of plates. You get over here in the Arabian plate, and you're going to get a lot of motion between the Arabian plate, and then you're looking at the African plate there. So every place along those boundaries, you're going to see lots of volcanoes and lots of earthquakes. Now, having said that, one of the larger earthquakes in the United States did not occur along that boundary or that fault line. Remember, guys, we live in the state of Missouri, and we have the Mississippi River, and right down that Mississippi River is New Madrid, and it's sitting right on the New Madrid fault line. Well, one of the larger earthquakes that we had in the United States was not due to the fact that it was on a crustal plate boundary. It was on the eastern side of the Missouri, and when it went off in the 1800s, it was large enough to actually cause the Mississippi River to go ahead and flow backwards compared to what it does today. So we know that just because we are not living on a fault line, right, crustal boundary plate, doesn't mean that we're not having a fault line under there. And we find that there's lots of faults that actually are all over the Earth. That one just happens to be a larger one, and lately seems to be a pretty active one too. So now, what can happen when crustal plates run into each other? Well, they can be pulled apart, and that's called a rift zone. They can burrow one under the other. That's called a subduction zone. They can slide alongside each other, and that's called a fault line. That's the one that you're probably more familiar with. Or they can jam together. Now, jamming is kind of an interesting word. Generally, jamming, you think they're going to run together. Well, they are, but they're just not moving real fast. But given enough time, ramming together, they will form mountains. Okay? So now let's look at what's happening at a convergence boundary plate. Well, you see that we've got one plate, in this case the oceanic plate, that happens to be going under one of the continental plates. Now, the continental plate then is moving over the plate that's in the ocean, and so you get a trench there, those kinds of things. You also get an area where that plate that's under the ocean will tend to get heated. So it's going to get heated, it's under pressure, it tends then, when it gets hot, goes ahead and melts. If it has a way of getting up to the top of that continental plate, then you go ahead and form lava, and that lava then will come out the top of that volcano. And because you have that oceanic plate moving under the continental plate, then you're also going to get a lot of areas of instability, in which case we're going to get a lot of earthquakes going on. So that's what happens when one plate is overtaking the other plate. Now, compare that to what's called a divergent plate boundary, and there you have two plates that are basically splitting apart. Okay? And so magma is coming up. That magma has been heated, it comes up, and it's forcing the two plates apart. Well, that's what's happening at the mid-Atlantic ridge. Okay? I've got a picture of the Earth. Okay? I've taken all the oceans away. And notice that you get what appears to be a big split down the middle of the Atlantic Ocean. It's kind of like the seams on a baseball. Well, what you're looking at right there is that big mid-Atlantic ridge, which is where I have two plates that are diverging away from each other. So you're looking at some of the newest real estate on the Earth because you're having material that is forming. So the Earth is pushing apart at that point. So someplace else on the other side is getting pushed together. Okay? Now, you can also see some of these other areas that look like the seams on the baseball, and that's where you've also got crustal plate interactions that are going on. But the big one is that North Atlantic ridge. Now, like I said, if you get that material that is molten, and it's going to go ahead and rise, it can come out of the top of either just lava plains, or it can come out of the top of a volcano. Now, hopefully, sometime in your lifetime, you will have get a chance to get pretty close to a volcano. You don't want to get too close, but getting pretty close would be kind of cool. So a volcano is simply a spot where the molten rock have risen to the surface. And those volcanic activities can either produce mountains or lava plains. The difference between a mountain and a lava plain is a mountain, then, think about what a mountain looks like, and you have that volcano given off from the top of that mountain. Or those lava plains are very, very, very large, and the lava just kind of wells up. Looking at Hawaii is a real good example of a lava plain. It just kind of opens up, and that lava flows out. Now, the Hawaii Islands, then, are an example of what are called hotspots. If I go back looking at those crustal plates that I showed you earlier, think about the Pacific plate. Well, Hawaii sits in the middle of that Pacific plate, and we know that that hotspot has lava that is coming up. Well, that's forming the Hawaiian Islands and the chains then of those volcanoes and lava plains that are going all the time. But the problem is the Pacific plate is also moving. So you get the island formed, it sits there, well, and gradually gets moved away, and so another island gets formed. And so that's why those things are continually active, because it's being carried along and moving at the same time that it's over that hotspot, which is continually producing more lava. Now, in general, not always, but in general, the volcanoes are found along those crustal plate boundaries. Now, guys, if you're looking at a mountain, it kind of looks really nice and peaceful, right? But we know that mountain in the past has gone off and produced volcanoes. So the main features of a volcano, you've got that magma chamber that produces the magma, rises up to the top. Sometimes it will come out in terms of an ash cloud, as well as looking at the lava flow. Sometimes you'll have a main vent. You might then have a secondary vent that comes out. You might have a secondary cone where that's coming out. You could have pyroclastic flow, which just means that it's flowing like a liquid, even though it's a combination of a solid and some gas and dust. You got that ash cloud that's a lot of times given off. A lot of times you will also have electrical storms. lightning storms, things like that around that ash cloud because of all the friction that's being created because of the motion in that. This is a nice dormant volcano, but you can see the tops of the craters of that volcano, and you can kind of see where lava has flowed down the sides. Now let's compare that with an active volcano. And the next several shots I've got are active volcanoes. Remember when I said it was kind of nice to be close to that volcano? I guarantee you those guys are feeling a lot of heat right now. But what they're doing is collecting lava to go ahead and study it. Okay, guys, what kind of rocks are going to be formed when those guys pick those rocks up? Did you tell me sedimentary rocks? Well, if you did, you were wrong. Sorry. Remember, guys, igneous rocks are formed from cooling molten material. It's another picture of a volcano with the lava flowing down. This one is more of a lava plain as opposed to the big mountains. And then if those lava plains or those mountains then get to the ocean, they drop off on the side, and you can see then they're going to be cooled immediately when they get into the water. And there's a lot of steam, all kinds of other things like that that are given off. And yes, those are some people at the top that are collecting as well. It's my understanding if you go visit Hawaii, you can take tours up to the tops of the lava plains. So if you ever have a chance to do that, that'd be pretty cool. Or you can take a helicopter ride and they'll fly you around the tops of the lava plains. Now, that's not a volcano. That actually happens to be a geyser out in Yellowstone National Park, but yet I put that geyser there because, number one, it's heated for the same kinds of reasons. There's molten material down below that is heating the water. The water builds up pressure and it goes ahead and releases. This happens to be Old Faithful, which goes off about every 57, 58 minutes. But the other thing is they think that that whole area around Yellowstone is an extremely old volcano, and that there is some indication that we may end up having another volcano right in the middle of Yellowstone Park. We know that Yellowstone Park is being uplifted on one side simply due to the fact that there is an extremely large lava mantle, that lava dome that is forming under one side of the park. Because if you look at the level of the lake there, Yellowstone Lake, one side is rising, which appears to make the other side sink. But really what's happening is just got one side rising because there seems to be that lava dome forming underneath. Will that thing ever go off? We're not sure. But there is some indication that at some point in the future, hundreds or thousands or millions of years in the future, that may indeed go off. Now I've got a website here. And this is a website that looks at Yellowstone, and it's right there at Old Faithful. And so when it gets to the point that Old Faithful is ready to go ahead and go off, this will go ahead and center directly on Old Faithful, and you'll be able to see a live version of Old Faithful going off. Other times you can see that there are other geysers that are around Old Faithful, and you can see them go off as well. So it's just a live webcam. It's kind of cool to look at. And when Old Faithful gets ready, they'll have a guide that'll go ahead and come on and kind of tell you what's going on. So now, let's look at the atmosphere of the Earth, because our atmosphere does tend to be very unique relative to all the other planets. Now remember that the energy that's going to power that weather does come from the sun, because that's where most of our energy comes from. Circulation patterns, however, on the Earth come from the rotational effects of the Earth and other geographical influences. So when we take into account what's going on with our circulation patterns and our climate, we have to take into account the fact that we have crustal plates, we have mountains, we have flat plains, we have all those things that are going to influence what's going on within our weather as well as our climate. And so what is the difference between climate and weather? Well, climate tends to refer to global patterns over decades of time, whereas your weather is what happens in your local region. So climate is long-term weather conditions. Weather is what you get from your nightly news on what's going to happen over the next week. And that's generally the only amount of time they're going to be able to give you a weather forecast. And even then, I'd be suspect on those last couple of days that they're giving it to you as a week at a time. So now, what's our atmosphere made of? Well, about 78% of it is nitrogen in the form of N2. About 21% of it is oxygen in the form of O2. And about 1% of everything else, like argon, water, carbon dioxide, all those kinds of things. Okay? Now, local concentrations may actually differ over a very short period of time due to a variety of things. Okay, the first night toward fall that it gets really cold and everybody goes ahead and starts burning their stoves, burning the wood, you'll get a pretty high CO2 concentration. Well, it's just people are burning wood. When you burn wood, you get CO2 given off. So things do change over time. If you live in St. Louis or Kansas City, where you're looking down at the industrial areas, then for short periods of time, you may look at some different concentrations. We know that those industrial areas sometimes produce acid rain. Okay? Well, those won't stay over long periods of time, but for short periods of time, they will go ahead and differ. But in general, 78% nitrogen. We breathe that in, we breathe it back out. Okay? 21% oxygen, which basically comes from biological activity. And then 1% of everything else. Now, just like the water cycle, guys, just like the rock cycle, we do have a water cycle. Basically says water evaporates, forms clouds, it rains, and it starts all over again. Now, unfortunately, most of the water that we have on the Earth is in the form of oceans, which means it's salt water, not fresh water. So one of the things that we need to try and make sure we do is reserve and preserve that fresh water that we do have. Now, that water concentration in the form of water in the atmosphere does produce part of our weather. And so we know that we have tornadoes. And I've got a picture of the United States right here showing Tornado Alley. Now notice, guys, we don't live in Tornado Alley. Even though we do have a significant number of tornadoes every year, we are actually not in that Tornado Alley there. We're a little bit to the east of it. And so that's what a tornado looks like, very destructive over a very short period of time. And so the next series of slides that I've got really just kind of show you some of the weather patterns that you're going to see in the air that consist of clouds, both storm clouds, all those kinds of things. Give you a different perspective than of what's going on in the atmosphere. Look at some of these clouds. Nice, really heavy storm clouds. Compare that to these really white, fluffy cumulus clouds. Just a series of thinking about what's going on in the atmosphere. Now look how that area that has changed due to the fact that you've got an island down there below. I mean, it's obvious that that cloud bank then is separated because of that island that's down there. Well, that island then is giving off a lot of heat, and the heat is what is causing those clouds to dissipate. So you get a nice clear view of the island. This is a swell coming in off the ocean. So that's basically a storm front. And you've got all kinds of looking at storms, thunderstorms, things like that within that cloud bank. Now remember I showed you a picture of a tornado earlier? Okay, this is a much larger storm called a hurricane. Now this is an interesting one because this is the start of a cyclonic storm, but what happened is it kind of ran out of energy and wasn't able to maintain its shape, and so it just basically dissipated. And so basically you're seeing the results of what used to be the beginnings of a cyclonic storm. So now, what are those parts of that atmosphere? Well, we've got the troposphere, the stratosphere, the mesosphere, and the ionosphere, which is sometimes called the thermosphere. So the troposphere, stratosphere, mesosphere, and thermosphere, or the ionosphere. Troposphere is probably the one that you're more familiar with. That contains all of our weather. That's where the clouds form. That's where commercial airlines fly. Not jets, things like that. They will go a little bit higher. But at least commercial airlines go ahead and fly. And for the most part, the temperature is going to decrease as the altitude is increasing. So you go up, it's going to get colder. Stratosphere, however, is where those cloud tops spread out. So sometimes you see these really big clouds, especially during the summer, and you see them go ahead and top out. They start spreading out. Well, they've reached the top of the troposphere or the bottom layer of the stratosphere. So that stratosphere basically is free of clouds. Now what we have is a gradual increase in temperature. And at the top of that layer, you have the ozone layer. And the ozone layer is, yes, that layer that you've heard about. We have a hole in the ozone. And what that basically means is the ozone is thinner at that area. And we worry about that because the ozone absorbs ultraviolet light very well. Okay, and ultraviolet light, if it gets to the Earth, can do some damage, especially the really strong ultraviolet light. And so we know that there are some problems because of the fact that that ozone layer is thinning. And we put chemicals up in the atmosphere that we didn't know at that time were doing some damage. We have now stopped putting those hydrocarbons and fluorocarbons, things like that, in the atmosphere. So we're looking at hopefully changing the fact that it is indeed thinning. Now, ozone, by the way, is an O3 molecule. Oxygen gas we talked about is an O2 molecule. Ozone is O3. And it's interesting that ozone is a pollutant at the level of the surface, but man, we really want it up there at the top of the stratosphere. What happens is that ozone absorbs the UV light, goes ahead and breaks apart into a free oxygen and O2, and then forms again. And so basically what you're doing is using that ultraviolet light within those chemical reactions to form and reform the ozone molecule. So that means it stays up there and doesn't make it down to the surface. The mesosphere temperature is gradually starting to decrease again. So we decrease, we increase, now we're gradually decreasing, and then we get into the ionosphere, or the top part of that. Well, that's the top part of our atmosphere. Now, guys, I want you to realize that that's not a level that you get to the atmosphere, the top part of our atmosphere, and then you don't have anything left. The atmosphere continues out, okay, and just gets thinner and thinner and thinner. The individual atoms tend to go ahead and escape into space. It's called an ionosphere because it's composed of ions. Those ions are charged particles, very high temperatures. Remember the shortwave radio signals, or just the old-fashioned radio as opposed to when you were doing nowadays on satellite? We tend to bounce the radio signals off that ionosphere so that you can go ahead and hear them. The ionosphere will tend to go ahead and fluctuate depending on whether it's a day or night. And if you remember, or if you are old enough to remember the shortwave radio sets, you could hear really long distances, pick up, things over in Europe or, Asia, things like that at night, because the ionosphere had settled and it allowed those radio waves to bounce at a greater distance because of the angle that it was bouncing. And then during the day, it'll go ahead and get energetic again and go ahead and climb a little bit. So that's where then those radio waves signals bounce off. Or they also are scattered at that level as well. Now, this just gives you a feel for what's going on within the 4 layers of the atmosphere. You get the troposphere down there, and you get the stratosphere, mesosphere, and then you get that thermosphere, and it just kind of continues going up. Okay, guys, so that kind of gives you a feel for what the Earth's like. And so as of the next section, we'll go ahead and start talking about Mercury, and then we'll just head out of the rest of the solar system. So with that, I'll talk to you then. Bye.